Hi, my name is Barry Turner. I'm the session chair for this part of the event, and I'd like to introduce you to Roberto Morano. Sorry, his presentation is CCS Corrosion and Material Selection: Overviews and Challenges. The approach of an integrated energy company. So Roberto works for BP. He's a material and corrosion chartered engineer with 20 years experience in materials, welding, and corrosion across a wide range of the energy sector. His main interests are environmentally assisted degradation phenomena, that's a mouthful, material selection, structure integrity for downhole, subsea, and topsides applications. He's been involved with the energy transition, corrosion, materials related issues since the beginning of his career. However, recently he's been appointed as the Materials and Corrosion Discipline Lead for the NEP project. And he's authored and co-authored around 50 contributions on materials and corrosion for scientific magazines and international conferences. So please welcome Roberto. Thank you.
Thank you very much. Can you hear me okay? Yep. So today I'm going to talk about one of the projects John has mentioned in his talk. Yeah, exactly. So it's a nice, continuity. It's the East Coast clusters, which is one of the CCUS UK clusters that we are working on. And let me start by thanking my co-author, Shokrolla Hassani, my colleague. He has helped me in preparing these slides. He is US-based, so couldn't make it. But today I'm standing also on his behalf. So this is the abstract. I think this has been circulated, so I would just crack on with the outlines of my presentations. I want just to introduce you to the East Coast cluster, giving you an overview on what it is. And then I will focus my talk today on more on the technical challenges and, of course, more on the corrosion challenges that we face in building up these infrastructures. I will give you a little bit of a highlights of the approach we have used in NEP, North Endurance Partnership Project, and I will conclude with some, indication of the gaps that are still to be addressed. There are many gaps to be addressed, and I think this need to be helped by the community altogether. So this is the East Coast clusters overview in a nutshell. I think the aims are to remove 50% of the UK total industrial cluster CO2 emissions, create and protect jobs in the Teesside and Humber regions, and establish that these two regions has globally competitive climate-friendly hubs for industry and innovations. It's a mix of different low carbon projects, industrial carbon capture, low carbon capture hydrogen projects, negative emission power and power with carbon capture. And as mentioned by John, this has been essential in the UK plan has been announced as critical on its path to net zero target. In terms of timeline, so in March 2023, the Department of Energy Security and Net Zero, DESNETS, selected the first 3 projects to be progressed in Teesside. And these were net zero Teesside power, H2 Teesside, and Teesside hydrogen CO2 capture. The first commercial operations are expected to start in 2027, so it's not that far. And in parallel, we have a new process that will come later in the year to enable further expansion, meaning that more projects will be sanctioned and allowed to progress into the next stage. The aim, again, is, in terms of number, is to capture and store an average of around 23 million tons of CO2 per year by 2035. And this will be obtained in steps, of course. Yeah, it works. The East Coast clusters is the whole of this, which is basically at the bottom we have the different projects, which can be categorized in terms of power generation, industrial, so the decarbonization of industries, hydrogen project, and bioenergy with CCS technology. These projects will be located in the Teesside area and in the Humber area, on the east coast of England. Then, on top of this project, we have what we call the Northern Endurance Partnership, which is the core of my topic today. And basically, this is the infrastructure that will be built to collect all the emissions from these different projects, and for transportation and eventually to be stored in a reservoir in the North Sea, which is the Endurance Reservoir that has been mentioned earlier. So all of this is the East Coast Cluster. Today I'm going to talk mainly about the NEP project. Yeah, I think I've covered this point. I think the last one is the sequencing process, which is basically how the government, the DESNETs, are going to review and sanction the different projects to be allowed to insist and use the NEP infrastructure. Okay, so let's have a closer look to how this is being implemented. This is the Teesside area, and this is a selection of the different projects that are at the moment considering to join the NEP projects. Among all of these, three have been selected, which is the BOC, Teesside Hydrogen CO2 Capture, this one. Then we have the NZT Power project and the H2 Teesside project. You see many other projects are in the slides, and they are still under consideration for the second wave of announcement, which will be later this year. Onshore in Teesside, NEP will build a gathering network, which is this dashed green line, which will be connected to all these emitters and will collect the emission from these different industries. This line is going to be a carbon steel line, and it's going to operate in gas CO2. We'll transport gas CO2, so we're talking about tens of bars of CO2. The CO2 collected will be pumped up in a compression unit here at the coast, and will be sent offshore through a pipeline, which I'll show you in some coming slides. NEP is all these transportation infrastructures. And this something similar in Humber. Basically, we have another bunch of projects that are willing to join the NEP infrastructure, although at this moment in time, DESNETs, they have not selected projects in Humber, but they will come later. We have another pipeline in Humber, which is again the green dashed line. This is very different pipeline from Teesside, because this is a much longer pipeline. In Teesside, we have something like 15 kilometers of pipeline. In this case, we're talking about 140 kilometers of pipeline, and it's going to be in dense CO2 and buried in particular. But the approach is the same. So the CO2 is collected at the pumping station, pumped up and sent offshore for injection. We have seen onshore. Offshore, NEP is going to be two pipelines, one from Teesside and one from Humber. Overall, we're talking about 150K from Teesside and another 100K from Humber. It's carbon steel pipeline and will process, of course, dense CO2, because in both cases we have dense CO2 that is sent from the different coasts, from the two different sites. The CO2 will be collected and injected at the endurance store, and an highlight on what we have subsea. Basically, we have the two pipeline reaching to two manifolds, and 5 wells to start with one extra well, which is will be used for monitoring purposes. In terms of quantity of CO2 injected, stage 1 will aim at injecting 4.1 million tons of CO2 per year, and this will be the first phase, which will be in operation by 2027. By 2030, the aim is to more than double this amount to 10 million tons per annum, and eventually by 2035, this number will go up to 23 million tons per annum. This is a first kind of offshore low carbon CCS infrastructure, at least in the UK, but even globally. And we have space for injecting CO2 in the aquifer. We have talked about the pipelines and the compression and pumping system to feed these pipeline. Of course, I forgot to switch the timer, so I don't know what I'm doing with time. Okay, I think we are right. Yeah. Let's get into the technical bit of the presentation, and it's going to be focused on corrosion, of course. And as a general context, so we're dealing with CO2, and CO2 itself is not a bad medium for corrosion, because we know that if we deal with dry, pure CO2, essentially is a non-corrosive media. And so it's not going to be a problem for carbon steel. The problem is that, as you have seen, I think we are dealing with industrial CO2, and industrial CO2 will be wet and will be impure for residual species that will be emitted by the different industries, and this will trigger corrosion mechanism instead. On this regard, so the first step to approach a corrosion safe transportation of CO2 is actually define what you can accept in terms of composition. You need to be sure that you develop for the different species that you can expect by the industries, these species are below a certain amount, so that you're confident that you are not triggering corrosion mechanism. So this is the first step in how we want to manage the corrosion issue. Of course, I mean, this is fine, but everything. So to obtain that entry composition, the CO2 streams will need to be treated by the emitters, and something can go wrong. So basically, you can have excursions. So you think you're dealing with a certain composition, but then some species may go off and may exceed the allowable entry. So I believe that the big difference between a conventional oil and gas projects and this project is actually that in oil and gas, you deal with something that you can manage and you know how it will evolve. So the corrosion media that you are transporting is known, and you can predict how it will evolve through the design life of your asset. In this case, you know that 95% of the time, possibly 99% of the time, you are transporting something that is not corrosive, but that 1% might be very aggressive, because the corrosion rates that you can get in with CO2 are very, very high, and sometimes in the double-digit area in terms of millimeters per year. In terms of corrosion, there are two main mechanisms that we need to talk about. One is the conventional CO2 and more known CO2 corrosion, which is basically only needs water. So you have water and you have CO2. CO2 dissolves into water and form carbonic acid, which is going to be very acidic and will corrode your metal. We can rely on modeling. I mean, CO2 corrosion in the oil and gas industry is very well known. The problem here is that we are dealing with dense CO2, not gas CO2. So the models we have are not really validated to those conditions. So you can, and in particular, you need to account for a difference with oil and gas, because in oil and gas you are transporting a certain liquid, and you have a certain ratio between this liquid and the metal surface. In CCUS, so the event that you need to deal with is actually that you have some water condensing at a certain site of your pipeline, And in that location, you will have a certain amount of water, limited, exposed with a very large surface area around it. And models are really struggling in predicting these conditions. On top of that, we are not really sure how this will evolve with time, because we have an active corrosion mechanism, but this active corrosion mechanism will deplete pretty soon, I imagine, because basically once you have this limited amount of water and the metal around it, the corrosion product will saturate your water and your corrosion rate will drop. But how fast and to what level is still kind of unknown. The other mechanism that we are facing is the so-called strong acid corrosion, which is triggered by a variety of other components, water, oxygen, SOx, NOx, and H2S. They can all react together, and they don't necessarily need water, because they can trigger a number of different chemical reactions, and some of these chemical reactions we'll see in a couple of slides can produce water. So they don't need water to be initiated, because some of these reactions will produce water. But at the end of the day, they can form strong acids, so sulfuric and nitric acid, which are going to be very corrosive. So for the first one, you need the CO2 corrosion, you need a certain amount of water condensing out from your CO2. For the second one, you don't need necessarily water coming out. You can just have, strong acid formation and condensation on your metal. What have we done? So I told you already that the first step is to define a composition of your CO2 with which you are confident, and you know that if you are within those limits, you are confident corrosion is not an issue. And that's the first step we took, basically. This was mainly done by, reviewing the work done over the last, this has been around for a long time. I mean, we're talking about decades. There are many projects out there proposing different, this is, for example, is the work from Morland, proposing different compositions under which you don't observe corrosive phase formation. Although I'm not able to share today the final composition we have selected for the NEP project, I draw your attention to the numbers of these tables. They are very low. So the challenge here is actually, even if you define an entry spec that is safe, you may need to deal with a monitoring system that must control your oxygen to be below 20 ppm consistently. And this gives you, two problems. One is a limit that can be easily overcome. And the second one, the technology to control this very low amount continuously, this very low amount of impurities is a challenge itself. But let's say that we have defined a safe entry composition. We need to now address 2 points. One, convince ourselves that indeed it is safe. So we developed it by literature, but we need to test it and convince ourselves that indeed it is safe. And secondly, we need to, simulate somehow excursions. So what's going to happen if you have a peak in oxygen? What's going to happen if you have a peak in NOx? And it's difficult challenge here, because you need to predict what could go wrong in something that has not been done in the past. The main answer to this question is actually that this is not something that you can do with one single activity. You need to approach the problem by different angles and come with a solution. And in particular, we did 3 things, basically. We used modeling. I told you that models are not up to date. However, there are very recent best-in-class models that have been developed, not available to the public domain, but that have been updated to include these reactions among impurities. And we have used it, but of course models will only tell you the thermodynamics of the problem, not the kinetics. So it will tell you that something is predicted to happen, but it might happen very slow so that you don't have it. And from this point of view, it's going to be conservative by definition, because it will tell you that potentially something could happen, but in reality that might not be happening. The second point is actually we have participated to several JIPs around the world on CCUS. There are many. I mean, it's very one like hydrogen, and CCUS I think is the most, JIP topic at the moment. We have selected some of them, and in particular, I will talk about one of them, which is in relation with the work by Morland. And basically, they have developed a device that is basically reproducing different gas mixture within an autoclave, in which you can look inside and you can see whether or not a corrosion phase is forming or not. So we move from modeling to actually real-life visual evidence if corrosion is happening. But again, you miss one last step, because even if you have something that is the first two bullet points are not telling you if something is happening, how corrosive it will be. So what is the corrosion rate? What is the impact on the material? And this is very condition specific, of course, which is the third bullet point. And it's basically testing in a more classic way at our own NEP conditions. So autoclave testings of metal coupons in this environment generated by the first two activities to see what is the impact on the material. In a nutshell, basically we model the problem, we observe the problem, and we quantify the problem. So again, it's a comprehensive way of getting tackling the topic. Highlights on modeling activities. Why is industrial CO2 different for pure CO2? Because basically, for example, if you look at this chart from Dagstad, this is water solubility in CO2 as a function of pressure, and you see the blue curve is pure CO2. The green curve is what happens if you have an impurity. So basically, the solubility is decreased. So if you have impurities in your CO2 system, it's more likely, it's easier to drop out water because you decrease the solubility. And by how much is a little bit of unknown, and at the moment there is test done. The problem is actually that you have many impurities, so try to figure out what kind of mix to test can be a very time-consuming testing approach. So that's why we screened at least these different scenarios by modeling. For example, the typical kind of output is how water solubility. So for a given entry composition, which is behind this simulation, what is the solubility of water in dense CO2 and gas CO2, so this is function of pressure, as a function of temperature. And these are the temperature that NEP could envisage. So NEP will move from very, very cold situations to warm situation onshore. Of course, the blue line is the 4C line, which is associated with the subsea pipeline. So this is the subsea temperature. One aspect to address here is actually that I told you that in NEP we have a gas pipeline and a dense pipeline. So the behavior of CO2 is very different because there is this discontinuity when you move from gas CO2 to liquid dense CO2, and the solubilities are really different between the two systems. So this is something that you need to deal with when you design the gas versus dense CO2. Another thing that we did, for example, again, for a given entry composition, you can play around and see what happens if you pump up oxygen. So you have concentration here, general concentration versus oxygen concentration. And you can model what is the expected amount of liquid phase formed. And you see that even for a given concentration, even at very low amount of oxygen, you can start forming, at least thermodynamically, this is modeling, water, which is the green line, and H2SO4 and sulfuric acid. Now, theoretically, this could happen. If it happens, it's the next step that you need to take, which is what we have done what they have done, for example, in this JIP. 10 minutes. This is the autoclave they've used. So it's an autoclave where you can inlet different gases and recreate gases composition inside, and you can look inside the autoclave, and basically you can resolve all these chemical reactions and basically visually see whether or not you have corrosion phases forming. And you do that by monitoring the inlet composition. You compare what you are putting it in the autoclave with what you are getting out. So you also monitor the composition of the gas that is leaving the autoclave. By this comparison and by the observation, if you have liquid forming inside the autoclave, you can basically understand what's the composition of that liquid. It could be water, it could be sulfuric acid, it could be nitric acid, it could be mixtures. And we have used these to basically test our developed composition. So we modeled, we observed it, but eventually we tested it. And there is a little bit to talk about testing, because of course at this moment in time, testing in CCUS environment is not really standardized. So everyone is taking different approaches, and this is a problem that I think the community needs to solve. So one of the big gaps to fill is having a consistent way of testing. But without sharing too much details, you can basically we tested, we quantified the corrosion, and we basically qualified our entry composition by obtaining very low corrosion rates. So even though we had indication from modeling that some acid could form, by the second JIP test and these tests, we demonstrated that this is very low, and the corrosion impact is is limited. There are some observations that you can make. Depressurization can be detrimental in testing, because depressurization, because of the large JT effect, the Joule-Thomson effect, can bring the temperature very low in your system, and even at very low water concentration, if you go down to -70, -80 Celsius degree, you can still drop water out of the system, and can mask your results. Oxygen, it looks like oxygen is key, so you need to be carefully now you manage your oxygen. And it appears, I mean, with the test that we have done, we have noticed that I think there is not, depending on the conditions, you can initiate corrosion at the bottom of the line or at the in other position of your line. So it's not because it's always said that if you condense a liquid phase, it will accumulate at the bottom of your pipeline. So that's the location where the corrosion will happen. We have evidence that that might not be always the case, although this is very preliminary results that will need to be further investigated. In summary, we have basically developed an entry CO2 spec for our system, the NEP project, which we have proven to be safe from the corrosion point of view, and we have done it by different streamworks, not only one approach. Gaps to be addressed. I think the first one is very important, define guidelines for reliable testing. We are not really much into sour service for NEP because of our particular composition, but sour service at very low pH is something that will need to be investigated in the future for other CCUS applications. How CRA and non-metallics perform in CCUS service again is a big area to be further investigated. Inhibition is something that could help, but again, there is a lot of work to be done there to qualify inhibitors for dense CO2. And not pretty much on corrosion, but also on the materials point of view. In CCUS, you will always need materials that will need to have very good toughness, and especially at low temperature, because you can have scenarios where the temperature is low, and you need to ensure that your material is tough even at those conditions. think that's it. The last slide is, this is from FAMSA in the US. You can go on the website. These are available on their website, so you can review this data. But basically, they are reporting the number of failures of CO2 transportation pipeline in the US. In the US, there are, a large amount of CO2 transporting pipelines, and it's been there for decades. So they have a good record. What I'd like to draw your attention is actually that with these, from 2010 to 2021, I think you don't have one single failure attributed to internal corrosion. The only failure attributed to corrosion are external corrosion, which is more, there is nothing different between a CCUS pipeline and a gas pipeline from the external point of view. But, and it's not, the worst contributor, because I think the worst contributor is non-threaded connection failure, so basically welds. Non-threaded connection failure, and basically associated with failure of O-ring and gaskets. So this is just a message to say that basically we are looking a lot into internal corrosion, but so far the US experience is telling something different. Although in the US the vast majority of CO2 transported is not industrial, and that's a key message, because most of it is from the food industry, for other industries, and is high purity CO2. So you need to put these numbers in context of what you are looking at. But it's interesting. And I believe that's it.
Okay.
Thank you very much.
Thank you. Thank you, Roberto. So we have a very few minutes for any questions, but probably the best thing to do is to talk to Roberto during the coffee break if you have a really long question. So if anybody has a short question that they would like to ask.
Okay, thank you very much, Roberto. Stephen Tate from Institute of Corrosion. You mentioned earlier about the use of corrosion inhibitors to control situation internally, but I just wonder, in your testing programs, have you been trying to use greener chemicals? Because there's a lot of pressure in the industry to change over to greener corrosion inhibitors.
So we are performing a corrosion inhibition testing, qualification testing program. I would say that we are not really looking into, that aspect is a little bit secondary at this moment in time, and just because, the inhibition we have in mind is not continuous inhibition, but it's going to be used just to solve temporary problems. So if you have a water excursion, and you have some water in your system, it's a temporary problem. It's not a continuous problem that you need to deal with corrosion inhibition. And we are investigating the use of inhibition to solve that temporary problem, which will be limited in time and limited in the amount of water to be treated. Yeah. So the volumes are very different.
If you're dealing with just peaks, you'll need quite a highly automated system to deal with.
It's very early days.
Yeah.
Yes, yeah. I'm not saying that we are that far with our analysis. It's just something that we started looking at, because potentially it's something that could help. And of course, it will help in pre-commissioning, where you inevitably will need to deal with fluids for a hydro test and these kind of things. So it might be that might help also in that part of the design life.
Okay, thank you very much. Thank you.